What's really cool about today is that we simultaneously get to learn things that are new and not new. I'll put it this way. The calculus we're learning is not new. The setup is. What do you think the newest word on the board is right now? Anybody see it? Like, what's the newest word on the board right there?
Polar.
Polar. Look at that. You just zoomed right in there. Good. So the newest word right there is polar right there. Polar. Has anybody worked with polar coordinates before? A little bit? Not in a long time. Do you have any memories of like either feelings or specific things from Polar Land? Anybody have any memories of Polar Land? Yeah, Getchell.
I remember we were given a challenge to
Yeah.
draw a picture on the polar graph plane or draw the coolest picture.
Yeah, so you can draw polar functions just fundamentally look different than the functions you've looked at. The functions we generally look at, Nathan, please put your surface away. I told you to do that. Now you're on record as doing that. Please shut the surface. Please put it face down. There you go. Thank you. Is they look different. They look different. Anybody remember how they look different? Like, what's something you can do with polar functions that you can't do with regular functions that we've seen? Yeah, they're described differently, but do you remember anything about the shape? Anybody remember anything about the shape of polar graphs?
It looks kind of like a flower.
You can make them look like flowers. Is it possible to write functions that look like flowers? Kinda, but what's the thing you learn about functions? They have to pass the vertical line test, right? Can they double back on themselves? Functions that we've dealt with can't, unless you break them into piecewise functions. Kinda, not really, and they get really hard. So we've been more limited than you know by how we describe points on a plane. We've described points on a plane traditionally as the x-coordinate right there, and then the y-coordinate right there. The horizontal position and the vertical position. In 2 dimensions, you need 2 pieces of information. In n dimensions, you generally need n pieces of information to describe a point in that space. There are other ways to describe the point in space. So what we're going to have here is this point xy, you can describe it with 2 numbers. One being the distance it is from the origin, which is going to be called the r value, and the angle that that ray makes with the x-axis going in the counterclockwise direction. The same direction your trig circles go in. So what that means is, if we look at a point, let's say u here. What's that in Cartesian right there? What's that point in Cartesian? Round to the nearest integer. In Cartesian, what is it? It's just 3, 4, correct? That's Cartesian points. If we want to do it in polar, first it's the distance from the origin. What's the distance from the origin there? 5. Are you going to be given lots of Pythagorean triples? Yes. It helps to have Pythagorean triples. Are you always going to be nice? Not always. What's the angle here? Is this an angle you know? It's not a nice angle. When I say nice, it's not a unit circle one. But how would you write it? If you had to write down a phrase that was exactly what this angle is, what is it? What is the angle? Oh, yeah. So, but is it exactly 57? It's not, but I give you props for remembering that a 3, 4, 5 triangle has an internal angle of about 57. How would you write it exactly using trig? Don't need laws. Pick your trig function. What function do you want to use? Tangent of 4 over 3? Tan inverse of 4 over 3. It's tan inverse of 4 over 3 would be the angle there. The inverse tan. Could you use inverse cosine, inverse sine if you wanted to? Yes. Generally speaking, we default to tan inverse because generally speaking, we're converting between coordinates. And generally speaking, what are we going to be starting with? Cartesian coordinates, which will give you what? The x-coordinate and the y-coordinate. Now, can you always find out the r value? Like, what is the r value in terms of x and y always? Can anybody tell me what it is? If you have x and y, what is the r value always going to be? Someone who hasn't spoken up yet. Anthony, if you were given x and y, just x and y of the coordinate, what's the r value going to be? You have a triangle, so how do you find the hypotenuse? Right, so in this case, it's you have x and y, and this is the r value. What's the relationship between x, y, and r? X squared plus y squared is r squared, so what's r equal to?
Square root of x squared plus y squared.
Yes, exactly. And then where did this tan inverse come from? This is tan inverse of y over x. So what we now know is theta is always going to be equal to the tan inverse of y over x. So if you're given something in Cartesian coordinates, can you always convert to polar? Yes. What we're doing right now is not calculus. It's straightforward trigonometry. Right now we're slogging through like trig inverse functions in honors pre-calculus. You could support your honors pre-calculus friends in their endeavor to survive. It's a good time. It's a good time. What about Q here? This point Q. Can someone tell me what it is in Cartesian? Someone new. Shirley, what is it in Cartesian coordinates? No, Cartesian is xy. What is Q? 5 what?
5, 0.
Yes, in Cartesian it's 5, 0. That's Cartesian. Can you tell me what it is in polar? What's the distance from the origin?
5.
And what's the angle measure?
0.
Yeah, so can they be the same? Yeah, they're the same when you're on the positive x-axis. They are the same sometimes. They're not on the negative x-axis because here, what's the Cartesian here? Negative 5, 0? But Sophia, what's the polar?
5.
Yes. And generally speaking, we're going to use radians. It's fine. Just generally speaking. I want to get you into that habit because the AP test, it's radians unless they say degrees. Radians unless they say degrees. So right now, have we done any calculus? Not really. We haven't done any calculus. We need the basics first. So the summary of what we've done is right here. One more point before we do that summary, actually. If this is theta right here, what's the sine of theta equal to in that triangle? What's the sine of theta? Y over what? R. What's the cosine of theta? X over R. So what does that tell you? It tells you that Y is equal to R sine theta, and what does X equal? R cosine theta. These are the first two like super important relationships that you need to remember. You're going to use a lot of. And polar functions are going to be, you plug in theta and you get out R. You plug in theta, you get out R. Our Cartesian functions, how do you graph them? You like scan from left to right. Like you make a table. It's like negative 10, negative 9, negative 8, negative. You scan from left to right, you plot points. Now you're going to be scanning from the positive x-axis, like a radar image. Like you're scanning all the way around. Like you're at 0 degrees, what distance are you? You're at 1 degree, what distance are you? You're at 2 degrees, what distance are you? You're scanning all the way around. So instead of left to right, you're scanning counterclockwise around the plane. So here's that summary, now that you've seen that. Here's the summary right here. You know that x is equal to r cosine theta and y is equal to r sine theta, and you know that r is equal to the square root of x squared plus y squared, and tangent theta is equal to y over x. Those are the four biggest things. Those are the four biggest things. But what does r equal? R is equal to some function in terms of theta. Now we can convert between them relatively easily. You just have to be careful about it. So for example, if this is in polar, I'm just telling you it's in polar, how would you convert it to Cartesian? Again, what does x equal? R what? R cosine theta. And what does y equal?
R sine theta.
Do you remember how when we worked with Taylor polynomials, I kept on having you write down Cn over and over again? Was that, just be honest, was that helpful in the long run? I hope so. Was it at least neutral? I hope so. So if this is in polar, how do you convert to Cartesian? What is x going to be equal to? What's the r value?
7.
That's the r value, so it's 7 cosine of,
5 over 3.
and y is equal to 7
Sine.
sine of pi over 3. Now, you need to not stop here, because those are nice trig values. Some people are, and you lose. Some people do, and you lose a point. What is cosine of pi over 3? Raise your hand when you know the answer. If this is something you hesitate on, you need to study your unit circle. Do not be that meme where someone's like riding a bike and then one little stick gets in the spoke and you go flying. There's that meme photo, right? You know what I'm talking about? Person riding their bike and like, I'm fine, and like, cosine of pi over 6. What's cosine of pi over 3, Anthony?
Root of 2 over 2.
Cosine of pi over 3 is not root 2 over 2. It is 1/2. And what's sine of pi over 3? What? Root 3 over 2. If you did not know these things, be honest with yourself and study. I'm just telling you, it is going to be monumentally hard and will slow you down tremendously on what we have to do. Polar is not that bad if you remember your basic polar rules, like logs. Are logs that bad if you stay within the rules? Not really. What do people do, though? They make rules up, and it goes poorly. So this is, right, so what is the coordinate going to be? The translated coordinate will be 7 over 2, comma, 7 root 3 over 2. Does that make sense? Okay, you need to be able to convert between the two. This is what polar graph paper looks like. It's the distance from the origin and the angle measure. And remember, the angle measure is always going counterclockwise, just like with regular trig. No, I don't know why they went counterclockwise instead of clockwise to begin with. Could all of math been done the other direction? Sure. Why do we call it x and y as our base default coordinates? Someone decided to do that, and then they went with it. It's just like a thing. Now, can you make this more granular? Yes. Can you turn on polar graph on Desmos? Yeah. It looks really cool. It's really fun to play around with, which we will do. Okay. So let's look at Cartesian equations. Let's just start without looking at the words and look at this right here. R equals 1. What does that mean? There's no theta. It just means that regardless of the angle measure, what's the distance from the origin? 1. So what is that? So you can convert it, but what is that? Tell me what it is in words. It's a unit circle centered at the origin. Because it's just the collection of points that are 1 away from the origin. That's it. So the simplest graph you can make in polar is just r equals a number. It's just a circle around the origin. Can you write that in Cartesian? Sure. What is it? So r equals 1 is the same thing as what? X squared plus. Now, which one is relatively simpler than the other to write? R equals 1. So that's the first reason we work with polar. Some functions, some shapes, are much easier to describe in polar than they are in Cartesian. And sometimes it's impossible. Okay, so we can go between the two. But let's make it more fun here. Instead, let's graph this. If I gave you y equals 1 in Cartesian, what does that look like? It's a horizontal line, y equals 1. Yay, that's nice. My question to you is, how would you write that in polar? How do you write this in polar? Anybody have an idea? Like, how would you write an equation for that in polar? Meaning, you're plugging in theta and you get out an r value. What would you do? Anybody have an idea? Yeah, Getchell, what's your idea? You're super close. But again, remember how when you were working with Taylor polynomials, I had you write down the Cn? What's the thing here I want you to write down? What does x equal? What does x equal? Thank you, Sophia. And what does y equal? R sine theta, right? What does y equal? What does y always equal? I can't be more subtle. It's about as subtle as my golden retriever Buffy. She's like, I want things, so she just goes lays on you and rolls over. Like that's how subtle she is, okay? What does y equal? So where do we put that? So what do you get? 1 equals r sine theta. So what does r equal? 1 over sine theta. So a horizontal line, in this case, is going to be r equals 1 over sine theta. And that should kind of make sense because here's the deal. At 0 degrees, does this ray touch this line? 0 degrees, the x-axis. Does the x-axis ever intersect with this line? No. What's sine of 0? Do not hesitate. What is it? 0. What's 1 divided by 0? It's undefined, right? So it's not defined. But if you go up a little tiny bit, what's sine of a little tiny number? Sine of like 0.01 is huge. Sorry, it's really, really small. What's 1 divided by something really, really small? So you need a big distance to go all the way out to here, and then a smaller distance, smaller distance. Oh, what's the angle here? What's the angle from here to here? From the x-axis to the y-axis? What's the angle? Pi over 2, correct? What's sine of pi over 2? Sine of pi over 2 is 1. What's 1 over 1? What is 1 over 1 over 1 is 1. You're right there, correct? So when it's really, really tiny, you need this long one, and then what does it do? It gets shorter and shorter, and then it goes back the negative direction. So when you write, if you're ever lost, please remember x is equal to r cosine theta, and y is equal to r sine theta. Yes? What do you think that... What do you think the general formula is going to be for the area of a polar function? We know the area of a sector is 1/2 r squared theta. Anybody want to guess what the general integral is going to be for the area? Yes, Getchell. 1/2 r squared d theta. Absolutely. And instead of going from A to B, we just call it we're going to call it alpha to beta, because these are not x values. What are these? Theta values. Where you're starting the scan and where you're ending the scan. Where you're starting the scan and where you're ending the scan. Help me remember to turn the recording back on when I pause it, everybody. That would be super helpful. The integration, there's no new type of integration here. You know parts, you know, what else do you know? Substitution. Yeah, the weird ones. There's no new integration method here. This is all setting up integrals and then knocking them out of the park, either by hand or just using your calculator. So generally speaking, how do you see this written? You see it written as 1/2 alpha beta r squared d theta. And r is going to be written in terms of what? What is r going to be written in terms of?
Wait, why is it r squared?
Because what's the area of a sector? This is the area of a sector right here. The area of a triangle is 1/2 r squared theta. So what we're doing is we're using that. This is the area. This right here is the area of a sector. So we're integrating little tiny theta value ones all the way around. I'm just going to tell you this right now. Generally speaking, in my opinion, the most common place people make mistakes on this is not the integration. What do I think the most common is for errors? Where does the error occur, do you think? Anybody want to guess? It's not the integration. That's really common. Yes. But also these. See this? Polar graphs can repeat themselves. Polar graphs, it's not a given that it goes around once. Sometimes it goes around twice before you know it. So sometimes you run the integral and then you end up with an answer that's double, triple, or some weird fraction of the actual answer. Be careful, because we're used to, in Cartesian land, limits of integration, are they relatively easy? Yeah, left to right. But is it easy to see when you're going all the way around? Not always. So here's one example right here, and this is the general one. It's really hard to come up with general rules because there's always an exception, and you just have to be super careful. Basically, instead of trying to remember a general rule, just check carefully. Does it work? When you're graphing things, what do I tell you is the simplest way if you're stuck on graphing something? What should you do? Do you remember what I've told you? Plot a point. Plot a point, plot a point, plot a point. I have kids try to do like the super complicated way of doing things when they could just do one point and then they'd be done. Has anybody worked with databases before? Like big Excel sheets? When you work with big databases, sometimes you need to audit, like Excel is the reason we have Wall Street, by the way, because it allows you to do big transformations. That's an oversimplification, but it's true. Side note, there's a World Championships of Excel. It's amazing. You can find videos. It's incredible. But similarly here, what I mean by that is sometimes people try to find complicated solutions when the data set is really small, and if they did it manually, they'd be done in 5 minutes. Similarly, if you're hemming and hawing of where something starts and where it ends, just plot a point. So if I wanted this area right here, it's going to be the integral alpha to beta of 1/2 r squared d theta. What does r equal, everybody? Sometimes will you have to build it? Absolutely, but generally speaking, they don't have you build polar equations. I've never seen them have you build a polar function on the BC test. They give it to you. So you plug that in, and what do you get? 1/2 alpha to beta of 3 sine 2 theta squared d theta. But what do you have to find now? Alpha and beta. Anybody want to guess or tell me what the alpha and beta values are? What do you start scanning at and what do you end at? Someone who hasn't maybe spoken here. Sophia or Daniel, what do you got here? Where does it start and where does it end? 0 to what? Yeah, it is 0 to pi over 2, absolutely. Because it starts here and it ends there. You can kind of see that, but is it a little harder than the other one? Absolutely. So plot a point. You could plug in 0. What's sine of 0? 3 times 0 is 0. So are you at the origin? Yes. Plug in pi over 2 into this. What's 2 times pi over 2? Pi. What's sine of pi? 0 squared is 0. You're back at the origin. But you have to be super careful. I can make the leaves be like spikier. So for example, it's not always going to be that straightforward. Check your limits of integration. Because on the AP test, what are they going to do? They're going to set you up with all the easy wrong ones. So what do you have to integrate here? 1/2 the integral from 0 to pi over 2 of 9 sine squared 2 theta d theta. That's not impossible to do. Is it kind of hard? Do you remember how we integrated the square of sine and cosine? The fact that you don't means it's not straightforward, but I'm telling you, you can do it. Generally speaking though, when they're testing you about polar, it's going to be things like, you're going to see right, but do not, like, what integral would you evaluate to do the area of this petal? And this would be the answer right here. Or they pull the 9 out. Or it would be a calculator problem, what would you do? Enter. Is there any extra credit for doing something by hand when you have a calculator on the test? No, there is not. Setting these up can be really nice, but sometimes evaluating them by hand blows up on you. Be careful. Now, what's one structure of this graph that's really cool? There's lots of symmetry, right? All of these petals are the same. So if I wanted to know what the area is of all 4 of these, do one of the petals and then what? Multiply by 4. Theoretically, could you scan all the way around? Yes. I would recommend highly abusing symmetry. So if you can do something once and multiply it, do that. It is really, really easy to mess up. There are going to be graphs that look like this that are going to go around like 3 times when you think it's twice and you're not looking at it. Abuse symmetry. Do 1/4 of it and multiply by 4. Do half of it and multiply by 2. Okay, everybody get up and stretch. Even when we have a petal like this, I might ask you, like, what's the slope of the tangent line at that point? Meaning, if I wanted to, I could ask you, like, what's the equation of that line in Cartesian? So we still need to know dy dx. If we have a function r in terms of theta, so you plug in theta, you get out an r value. How do you find dy dx? Well, it's very, very similar to parametric equations. Parametric equations, how are they defined? You plug in a t value, you get an x value. You plug in a t value, you get out a y value. Do you remember how we found dy dx when we were dealing with parametric? Do you remember how we found it? It was what? In parametric, what was it? Do you remember? dy dx was equal to what in parametric? Dy dt over dx dt. So what do you think it is now, dy dx, if it's in polar? Anybody just want to guess? It's pretty much identical. dy d theta over what? dx d theta. That's all it is. And what, again, remember, what does x equal? What does x equal? R cosine theta. And what does y equal? R sine theta. So if you have these pieces of information, it's pretty much identical to what you did in parametric. The differentiation becomes a little bit more complicated. That's it. But this is not new. This is not new. It's very, very, very similar. Instead of t, we're plugging in theta. So this is what you see. You see this. When they say f of theta, you can say r of theta. It's just the name of the function right there. It's the distance from the origin. So dy dx, does this look familiar? It's the same, right? So let's go back to our petal, though. Let's see what happens. I drew this, and I could ask you, like, what is, let's call that point r comma pi over 3. Because let's just make this angle right there. That angle right there is going to be pi over 3, so it's 60 degrees. So I could ask you, like, what is the slope of the tangent line there? It's a relatively straightforward ask. Does it mean it's easy to find? It's a little bit harder than it seems. It's a little bit harder. Here's why. Let's use this function. We have r equals, I'm going to draw it over here, and we'll put it up here. We have this petal right here, and we know it's r is equal to what? 3 sine 2 theta? Was that it? Okay. You with me? So what does that mean x is equal to? 3 sine 2 theta times what? Cosine theta. Do you see this, everybody? That's the cosine. This is the r value right there. What does y equal? 3, 2 theta times what? Sine theta. Does everybody see that? Here's the sine, and here's the sine, and here's this. Everybody with me? Well, following this definition isn't that bad. Following this definition isn't that bad because you know, look in the top left there. What does dy dx equal? So dy dx is equal to this. So what do we need to find? Right. Now, when we want to do that, we therefore need dy d theta. Do that right now. You can do it on your surface. If you want a marker, I'll toss you one. Do dy d theta. Do that for me right now. Seriously, on your surface right now, find me dy d theta. Did people get that? Or something like that, I hope? Because you had to use the product rule, everybody. Derivative of the first times the second plus the first times the derivative of the second.
Oh.
Yeah, And then do you get something similar for dx d theta? Yes. And then what do you have to do? Plug in what? Pi over 3? Is that a trig value that you should know the answer to?
Yeah.
Yes. Is this really annoying to do by hand? Hold on. Is this really annoying to do by hand?
Yes.
Yes. Okay. Getcha, you think there's an easier way. What is it?
I think that dy over d theta is equal to the sine of theta plus 2 theta. Okay. Wait, plus the 6 and 3.
Wait, I'm sorry. So my guess is you futzed around with this because you wanted to try to get something simpler?
No, I see. It looks a lot like the sum of...
It does. Here's the thing. Be careful. Be careful, be careful, be careful, be careful, be careful. Do the easy. Don't meander off, okay? I understand it can, but here's the thing. Can trig things look a lot like something you want them to, but really not be those things? I agree. It looks like the sum of angles or something like that. Be just really careful.
Yeah.
Because if you know your basic trig, should you be able to plug in pi over 3 into this
Yeah.
and get an answer in like 10 seconds? You should. If you can't, you need to study your unit circle.
Yeah.
Do you do something similar for dx d theta? Yep. You get something else. And you get this right here. And then what do you do with these two things? You plug in, you get an answer, and then you get the division, and you get your final answer. Is that annoying to do by hand? Yes. On the AP test, I've never seen them do something this annoying by hand, but if you have your calculator, should you be able to do this in 10 seconds with your calculator? Yeah, you need to be able to. Make sure you're in radians, you plug in the calculator right, and you're good. It's not. Does it look like something you've seen before? Yeah, it's arc length from parametric. If you want the distance between 2 points, what do you need? The base squared plus the height squared of the triangle equals the distance squared. Do you literally have the horizontal shift? Yeah, dx d theta and dy d theta. Now, here's the thing about this one. This is just a direct application, Babylonian theorem, a triangle, a squared plus b squared is c squared, right? Here's the thing. I could ask you, for example, using this formula right now, what's the length of the edge of the first petal we just looked at? What's the length of the edge of the first petal we looked at? That's what this question is asking right there. R equals 3 sine 2 theta from 0 to 2 from pi over 2. So that's literally, what's this distance? Did you find out what dy d theta is just now? Did I ask you to find dy d theta? Yeah. Is it big or small? What is it? It's a little big, right? Could it be bigger? Sure. Is dx d theta similar sized? Yes. What does this formula have you do? Square both of them and evaluate the integral. Is that something you'd ever want to do by hand? Just say no. Just say no. Is that something you might need to do in your calculator? Yes. Because what they will have you do is they will have you do this and then do some basic simplification and give you 5 answers that look really similar, but only one of them is correct. It's annoying. I'm just preparing you for that, okay? It's going to be annoying. It'll change by, there'll be a 9 in front of it, there'll be a 6 or a 4, it'll be negative, positive, and you're like, I don't like this. But there's a really cool result of this. There's a really, really cool result. What's the simplest polar graph that I've shown you so far? What's the simplest one? R equals 1, right? That's a unit circle, right? So I could ask you, if R equals 1 right here, what's the distance you travel if a bug walked on the edge of that circle? I could ask you that, and let's use this formula. It'd be 0 to 2 pi because you're going all the way around, right? R equals 1. So what does x equal? 1 cosine theta. And what does y equal? 1 sine theta, correct? What's x prime in terms of theta? Negative sine theta, right? What's y prime in terms of theta? Cosine theta, right? The formula for this was the square of the derivative of both of those. What's negative sine squared? It's just what? Plus, what's cosine squared? Oh, it's cosine squared. What's sine squared plus cosine squared? So what do you get here? The integral from 0 to 2 pi of just what? 1 d theta? When you integrate that, what do you get? You end up with theta from what? 0 to 2 pi, so that's just equal to 2 pi. Oh, is that the circumference? Is that the circumference of a unit circle? Yes, yes it is. Well, let's generalize it a little further. If I have a circle of radius r and I want to know what's the distance all the way around this, let's do the exact same thing. What's the integral going to be? The integral from 0 to 2 pi, but in this case, what does x equal? What's the definition of x? I want you to write this down like every time. X is equal to r cosine theta, and y is equal to r sine theta. This is a constant in this case. This is just a constant r. So what's x prime, Daniel? What's x prime of theta? What's that one going to be? R times negative sine of theta, right? And what's y prime? R cosine theta. So what do you do with those two things? You square them and put them inside, right? So what do you end up with? R squared sine squared theta plus what? R squared cosine squared theta? What can you factor out of both of those things underneath the radical? What's in both of these things? R squared times what? Plus? Oh, what is this right here? What's this? That's just 1. So what do you end up with? 0 to 2 pi of r squared d theta. So what is that? 0 to 2 pi of what? R d theta. And r is a constant, everybody. R is a constant. So where can you bring it? R times this d theta. So what is that equal to? R times what? Theta from 0 to 2 pi. What's that equal to? 2 pi r. What did we just prove? Circumference of a circle is 2 pi times the radius. You just proved that the circumference of a circle is 2 pi times the radius using polar arc length integration. So not quite the same thing as when you learned it in, like, I don't know, Algebra 1 or wherever you learned the arc length. It's pretty cool. It always bothers me when we do these proofs and we get something wrong and then you have to find the error. It's a lot. On Desmos, what you can literally do is just, you can type out the words of the variables you want. So like, ready? Like r theta, look at that. You see what it did there? Equals 3 sine 2 theta. Like, oh, look what it did. There it is right there. And look what it puts down below. It puts the domain restriction. So like 0 to 2 pi. So one thing that's funny is you could do 0 to pi divided by 2. There it is. Which pedal goes next? Second, third, or fourth quadrant. If I went from 0 to pi, which pedal do you think is going to go next? We think maybe, you would logically think second quadrant maybe. Check this out. 0 to pi. No, it goes to the fourth quadrant. And then which one do you think it's going to do? Pretty cool, huh? So this is what I mean about being not obvious. Like, we think of scanning things like this. Is it always going to be built that way? No. And then 2 pi. What happens if I put in 4 pi? It overlaps itself, right? Because the period repeats every 2 pi. You have to be super careful about this. But this is really fun to do. Also, up in the upper right, if you hit the wrench icon, you can change it to this. And there's your polar graph paper right there, which is pretty cool. If you're ever lost about how to do something with Desmos, what should you do immediately if you're ever lost about how to do something in Desmos? There's something really cool you can do. It's super simple. What do you do? Like right now, I'm not sure how to plot a point in polar. What would I do? What should I do? Open up a new tab, type in the sentence of what you want to do into Google, and put Desmos in front of it. somebody has a page up like this that does the thing you want in Desmos, and you can see immediately how to do it. So you can plot points in Desmos, move things around. One thing that's fun here is, have you ever done this before? You can change like this to A. Add a slider for A. And then change this to B. And add a slider for B. Have you worked with sliders before in Desmos? Have you seen this? This is really cool. So look, I'm going to zoom in a little bit here, right? And then what you can do is like you can change B to like 2. What happens? Oh, that's what happens. What happens if I change it to 3? 4? What happens when I change A? What do you think happens to the graph? What does A do to the graph? Yeah, it's the amplitude. It kind of gets bigger from the origin. So I go to 2, makes it twice as big. Play around in Desmos. It's super awesome. You can change the colors, all sorts of stuff.